Okay, I started recording. So, welcome to the class. We will be talking today about signatures based on discrete logarithm problem, and it will be based on zero knowledge proofs. So we'll introduce these concepts of the zero knowledge proof of knowledge. It will not be a full-fledged lecture on zero knowledge in general. If you want, you can continue in a advanced crypto class next quarter, where we'll go over. This would be, the first topic actually we should handle. We'll handle, but here is like a little, preview of this concept and its application to signatures. Let me start with okay. I'll switch a camera to a document camera, and okay. So let's quickly review what is a signature scheme, so that we know this will be our target. Let me check if you can see anything and you can't. So let's focus. Okay, sorry, it somehow did not focus. So let's try to again. Okay, it's not focusing. I'm not sure why it usually focuses. Somehow not this time. Oops. Oh, okay, great. It focused. All right. So a signature scheme is a triple of algorithms: key, generate, sign, and verify. With the syntax that a key generation generates a pair secret key, public key, and it's a randomized algorithm. And nominally, we give security parameter as input to the key generation algorithm, so it knows what security parameter it should generate these things for. So, like for example, in RSA case, sizes of a primes that make RSA modulus. In the discrete logarithm case, just some multiplicative group of sufficient order, group of residues, or elliptic curve, right? Like we have seen these two examples. But there are other sources of signature schemes from other hard problems in computer science, for example, lattice problems. So a signature is given a secret key and a message, and it outputs a signature. Signature sigma. Verification takes the public key message and a perpetuated signature and outputs 0 or 1. And correctness is that for every SK PK created by a key generation and every message in a message space designated by the public key, which could be all bit strings, but it could be restricted. If a signature is generated by the signature algorithm on a given public key, then the verification works. In other words, it outputs 1, except for negligible probability. Okay, so Okay, and a security notion, again, we have to recall this, is existential unforgeability under chosen message attack, which goes like this. Random secret key public key pair is generated. Adversary gets the public key. He has access to a signing oracle that has the secret key. The oracle sends signatures based on the secret key of whatever message adversary likes, and adversary outputs a message signature pair, and he wins if, first of all, this is a correct message signature pair, right? So it verifies under the public key, and secondly, the message is not in the set of the messages that were queried here, and this is done q times, right? So there's m1, m2, all the way to mq for some q that is polynomial in the security parameter. Okay, so that's what we need, and we're going to go that I want to show you today is how to if it would be a signature with existential unforgeable CMA security from the discrete log assumption.
Professor?
Yes.
So far, signature is just a MAC with a public key studied?
No, so that's what we said last time. That oh, okay. Sorry. Yes. So okay. Sorry, I thought that you can. I thought you said that we can implement it as a MAC using a public. No. Yes. So it's the difference between signature and a MAC is the presence of the public key, and the fact that the verification involves the public key. Right? So there is some public way to verify. And a MAC had no such thing, right? So a MAC had a single key, right, and the only person who could verify was the one who has the key. So if I give people ability to verify, I also give them ability to sign. And here the two are different. There is a key that allows signing, and there is a key that allows verification. And this one can be published to the world, in particular adversary knows it. And everybody can do verifications, but it doesn't allow them still to forge, right? So it's similar as public key encryption, where it's really the presence of the public key. And in the case of encryption, the presence of the fact that an encryption algorithm takes the public input, and only decryption takes the private input.
Okay, thank you.
Yeah, so we would like to have signatures from a DL assumption. So can we have it similarly to El-Gamal, that the secret key is X and the public key is G to the X, where X is a random exponent chosen in this group, where G and G is a generator of group G of order P. Okay, so you have some multiplicative group and its generator, and the way you pick a secret public key pair is, and we will call this value Y. Okay, so a secret key is X, the public key is Y, G to the X. That's the setting of a Diffie-Hellman key exchange and of El-Gamal encryption. So can we use the same setting to sign? So we would like a signature to be some operations that you need this. So you verify under key Y, but the trapdoor that allows you to sign is the discrete logarithm between the public generator and the public key. And this stuff, the generator and the group, is assumed public parameters, just like in the case of the Diffie-Hellman or El-Gamal. And so is the prime here that tells you what's the order of the group. So if Y was a public key, and if indeed X was the only way to sign, then we would have hardness based on discrete logarithm, because if we could show that the only way to sign is to compute X, which is a discrete logarithm, well, then that is hard by the discrete logarithm assumption. So the idea for the signature is that signing will be like proving knowledge of the discrete logarithm of X, which is defined as a discrete logarithm between the public parameter and the public key. And verifying would be like verifying the proof. Okay, and this proof of knowledge of the discrete logarithm has to involve the message somehow. Okay, right? Because it's not just that you're proving that you know the discrete logarithm, it's you have to do that and somehow bind this proof to the message. And the verifying of that proof should need only G, Y, M, and the proof as inputs. Okay, so this is public. This is the public key, right? So the verification is supposed to take the public key, the message, and the signature. The signature, so signature sigma will be the proof. Okay, and this is the sigma in the signature verification equation. So that's the top level idea, and of course we have to specify what is this thing that you can prove knowledge of something. We didn't have such a toolkit in our cryptography, such a tool in a cryptography toolkit so far. This will be exactly the zero knowledge proof here, and intuitively, see, one way to prove that you know knowledge of something is to just sense this something. And now everybody can verify it, right? Because everybody just, if you know X, then you can exponentiate it to the X and check whether it's Y. So it's a trivial implementation of a proof of knowledge of something. Just give that knowledge up. Clearly, this would fail to be secure, right? Because if a signature simply involves the secret key, then in a trivial way, this guy now has all the trapdoors. He just performs whatever signature operation using the secret key was. So the proof that is the signature must in some way prove it, but hide information about the secret key. And that's why this proof for CMA security, it needs to be a zero knowledge proof. Okay, and what this notion of the zero knowledge proof, what it will capture in in some way, is that the proof is performed with the knowledge of the discrete logarithm, in this case, as input. But the proof in some way hides this input. It's zero knowledge, as in it does not leak what in this application is a secret key. And what this notion will capture is that it doesn't leak it in a sense that these proofs are precisely useless in order to create anything involving the secret key. And that's the notion of uselessness that is needed here. These signatures must be useless in creating an operation that involves the secret key, right? That would, namely the signing operation. It is very similar. We have seen this type of reasoning before, when we argued that decryptions in a CCA secure encryption scheme, you can query the decryption oracle and get decryptions, and they are useless in determining left or right encryption challenge, whether the M0 or M1 is encrypted in the case of encryption, right? So we have ways to argue that something is useless. Replace it by a in a similar way. Because why was this decryption useless? Because they could be emulated without knowledge of the key. We simply always reject it unless it was created by the correct encryption oracle. Last time I very quickly went over basic blueprints for how to create a CCA secure public key encryption, where the reasoning was, we use different reasoning in these cases, but we only cache them. But you have seen these type of arguments before, and now you will see them as a zero knowledge. So this is a motivation for what we will do next. Okay. So here is a notion of. So first, what is an interactive proof in computer science? So you have some language, which is L is a language. It's a subset of bit strings. Some bit strings are in the language, some are not. So, for example, L is a subset of satisfiable Boolean formulas. Some formula given to you encoded in binary is satisfiable, some is not. And you might remember that this is an NP-hard problem. So in general, there is no polynomial time. Okay, so the only way there could be polynomial time algorithms to solve this problem, to determine whether a formula is satisfiable or not, is if all non-deterministic polynomial time computation can be done without in a deterministic way. But we would be concerned in a cryptographic context. Here are the examples of very useful languages. For example, a language of a public key and a ciphertext and a message, such that there exists a randomness, such that the ciphertext is the result of an encryption of this message under this public key using this particular random string. So if you have a public key encryption, you know it must be randomized. And in general, if you have an indistinguishable public key encryption, then if you see a ciphertext and a public key and a message, if these are generated with correct distributions, right? Correctly distributed public key, random encryption, and arbitrary plaintext, you cannot decide whether what is encrypted here. In particular, you cannot decide if that message is encrypted here. If you could always decide this, then the encryption would be not CPU secure. So, but if there exists randomness, right, then it's still, you know, some ciphertexts are encryptions of this and some are not. So some bit strings that encode this will be in this language and some bit string will not. In general, okay, or here is, okay, that's enough. So this is language 1, this is language 2. For all these languages, note, languages, for every statement in the language, there exists a witness W, such that statement is in the language even only if, okay, so there, for all these languages, there is an efficient verification procedure, verifier, let's say V, you know what, the efficiently verifiable relation such that for all statements in the language, there exists a witness such that the statement and the witness are in this relation. In the case of L1, witness for a statement is a satisfying assignment. And the relation is simply a pair of formulas and assignments which satisfy these formulas. And it's efficiently verifiable because if you have both the formula and the assignment, then you know, you assign what the assignment tells you. This variable has this 0, this variable is 1, this variable is 1, this variable is 0, etc. And then you just verify that the formula is satisfied. So this is a fast procedure. The point is that exists some way to prove that the statement is in the language. Just publish this assignment. Likewise here, W for a statement is the randomness R used in encryption. Actually, or the secret key corresponding to the public key, right? In fact, I have two different witnesses. My witness could be the randomness I used to encrypt, that was used to encrypt. Now, given the statement has public key ciphertext a message, given the witness, this verifiable relation, efficiently verifiable relation is, okay, just plug it in and compute forward and check. So yes, it's efficiently verifiable. If you have a secret key, there's a different verification formula. It just takes this ciphertext, decrypts it, and checks whether it's equal to M. And moreover, also checks that the secret key corresponds to this public key, right? So we call them witnesses because, yes, there is a public statement, and there is some string that witnesses to the fact that the statement is correct, that it is indeed, this encryption is indeed an encryption of this message. You can think of cryptographic applications like an escrow. You're supposed to encrypt this message and now prove that you have. Okay, maybe once you proved it, then we can store this cipher as the escrow of your, but you can prove it. If you prove it in zero knowledge, then you don't, for example, give out any information about your witness. Perhaps your witness is the secret key. Okay. And of course, we'll see an application to signatures. Okay, so an interactive proof is a procedure that involves a prover whose input is a witness, and a verifier whose input is a statement. And we assume that statement and witness are in this relation R for language L. Okay, and interactive proof is some protocol between these two parties. What's an example of a protocol? Key exchange, right, is an example. It's some interactive procedure. These parties use these inputs to send to each other messages, and at the end of which verifier outputs 0 or 1. Okay, and this stands for reject, and 1 stands for accept. And I want two properties. First of all, that it's called correctness. That if statement and witness is into relation, and therefore a statement is in the language, then probability that the verifier who runs on this statement as an input accepts is it's either 1 or it's 1 minus negligible. Although I might have some larger error for some initial scheme, and then I want to compile it, for example, by repetition or some other way of combining to reduce it, this error, to a negligible one. But this is my end goal. And the second property called soundness, which says if the statement is not in the language, and in particular, therefore, there exists no witness for it, then no matter what the prover, for every efficient algorithm P star, probability that, so what do we mean here exactly? The probability of V accepting in interaction with a prover on W. Okay, so this is V would input a statement, he interacts with prover on input W, and at the end we just care about the verifier output, and we want this to be at 1 minus at most negligible. But in the case of soundness, we let the verifier talk on input statement. So we are looking, what's the probability that he accepts in interaction with P star, who, for example, knows the statement as well. It's the wrong statement, but without loss of generality, he knows it. And we want this to be at most negligible, right? Because what this means, okay, you have some procedure. The verifier basically does not know whether the statement is correct or not. It's some formula, and if this if you believe it's hard for polynomial algorithms to decide this, then an efficient algorithm will not be able to decide this, at least for some cases. And if you believe that encryption is CPA secure, then if I generate this with proper distribution, then it's equivalent to basically saying there is no efficient algorithm who can just decide this locally. But through some magic protocol that with an entity that knows the witness for this guy is going to either accept or reject. By correctness, it has to be that he will basically output only accept, except from negligible probability of error, if he is interacting with somebody who knows this witness, and therefore, in particular, the statement is true. But if the statement is not true, then no matter what this guy does, what kind of responses it sends, verifier would output a 0, except for negligible probability. So the notions of interactive proofs are interesting in computational theory. In particular, there are problems which, for example, they are in P space, which means that it takes the P space. Yeah, hold on a second. Yes. So basically, we know of no efficient algorithms to even verify the statement, even if you knew the proof for it, the witness for it. But if you talk to some oracle who had, okay, let's say infinite computing power, then that oracle could give you like advice that is short. And given that advice, you will be able to determine whether the statement is so true in an efficient way. That is surprising that access to some interactive oracle allows you to decide with these two properties. But in the case of cryptography, these two properties are sort of not sufficient, at least in the application of a signature scheme. I need a third, because what I need is, to somehow stop. What about this? Basically, does not. What about a proof, which the prover on W simply sends W to the verifier, and the verifier locally output 1, even only if the relation between the statement and the witness holds. Okay, it's efficiently verifiable relation. This witness prover has, so why doesn't he just send it? It satisfies correctness, it satisfies soundness in a trivial way. And it would definitely not do right here, right? Because if my signatures are proofs, I cannot send the witness to the statement which I'm proving, which is a knowledge of discrete logarithm between here. because that's just revealing my secret key. So that's where the zero knowledge property comes in. So here is the third property that we would like. It's zero knowledge. And the property is this, that there exists, so for every efficient V star, so cheating verifier, note soundness was phrased in for the case of a cheating prover, right, who somehow sends wrong messages and tries to dissuade the verifier to accepting, even though the statement is wrong. Zero knowledge will flip the picture, consider dishonest verifier, and ask that whatever prover does, it somehow keeps privacy of the witness. Okay, but keeps the privacy up to leading to this bit. So in other words, somehow we must capture that the only thing that this learned from here is the fact that the statement is true, and therefore the verifier should accept, sorry, but nothing else. So we'll capture this with a notion that for every cheating verifier, there must exist an efficient algorithm sim that stands for simulator. And such that and here first let's say it informally. So V stars interaction. Okay, sorry. Such that for every statement and witness in the relation, therefore also for every statement in the language, right? Because we said that we are going to look at languages, which, by the way, I didn't use that phrase, but they are called NP languages. Any language that has an efficient relation like this, it's called NP language, because these are all languages in NP, because the witness is supposed to be polynomial time. The size is polynomial. Why? Because it's an efficiently verifiable relation. So definitely the input to the verification equation must be polynomial in the size of the input. And a non-deterministic algorithm, given the statement, will be able to solve whether or not the statement is in the language. Using non-determinism, it just shoots in the dark for bits that describe a witness. One of the non-deterministic paths of this non-deterministic algorithm will lead to the correct witness if the statement is in the language, right? Because if the statement is in the language, then there exists a witness. The size of the witness is upper bounded by some polynomial. That's the search space, the depth of this tree. And so this is a characterization of all NP languages. Yeah, and you know, these notions for us would make most sense in when specialized to case of NP languages. So if a statement is in NP language, then it has a witness. And for every statement witness pair, the interaction of the cheating verifier with the prover who has input W, and the cheating verifier on he also gets an input, the statement, but he interacts with the prover who has this witness, and the prover is an honest guy. He keeps on proving things to people. That's for example here, this will be a signature oracle. It would, if signing is like proving, so every time adversary wants something proven, this signing oracle will run the prover algorithm. And we are concerned with the verifier in this case, learning something about the witness and want to limit what it learns. So that's exactly the case here. The verifier is a cheating verifier and he interacts with an honest prover. And we want to say that this is computationally indistinguishable, this interaction, from an interaction of V star on input ST with the simulator, whose only input is the statement ELSO. Let's see this pictorially. So here is the verifier, and he potentially cheats in this protocol. In other words, what does it mean, cheat? He sends arbitrary messages. The standard protocol says, what you're supposed to do is, I don't know, send bits of this statement. But the cheating guy doesn't do that. He sends some other bit strings, possibly to extract information from the prover. So here he interacts with the prover, and they interact. Let's say the protocol has 5 rounds, and there's some view of this interaction that V star has. And we want to say that this view is indistinguishable from a view that is executed by a simulator. Well, before we ask, like, how is that possible? Let's see that it would be useful, because if this is a signature and the idea for the signature scheme is that signatures are proofs. If we knew that prover, whatever prover produces, can be emulated by an efficient machine that doesn't know the secret key, it can emulate what the prover does on the knowledge that is a public knowledge in this case, because the statement in this case will be made of the public parameters and a public key, and a statement, and I guess a message also. So the statement in this is that that it's all public information. If the prover can be replaced by the simulator, then we would be able to replace this by a simulator that uses public stuff like public key and a message, basically. And if that is so, then this would be the basis of saying that, it was not useful. Because if adversary interaction with the real signing oracle could be simulated by this efficient simulator, then all of this stuff, therefore, would be like some modified adversary just do it locally. He gets a public key and he locally emulates these signatures. And if no efficient A can detect the difference, playing the role of the cheating verifier here, interacting with this prover, then therefore replacing this with this will not change the view. And therefore signing is not needed because it can be locally emulated. And therefore now this proof, the signature security is much simplified. It becomes a question, given a public key and interaction with no one, the only thing you can do is now use the public key. Can you present a message signature pair? And you can believe that that's going to be much easier task than having this thing, having these interactions around. So, okay. So, okay. There is much to say about like what exactly, in what sense this is possible at all. So I will tell you very briefly what is the gist of the idea that allows this, because if you contrast this now with the properties required of this proof system or before, namely correctness. Correctness said that if statement is wrong, then the prover has no possibility of convincing the verifier. But zero knowledge said that whatever prover does can be publicly emulated. So what stops this public emulation to execute on the wrong statement? And if execution on a correct witness is indistinguishable from execution on the correct statement, that's the first step. But if correct statements and incorrect statements are indistinguishable, then executing the simulator on the right thing and executing him on the wrong thing also does not help. Because if you could distinguish execution sim on correct ST and execution sim on an incorrect ST, then you can distinguish correct and incorrect STs. Just run a simulator on them. So therefore you can't. So therefore the verifier, in particular, simply the honest verifier, right? Because this is arbitrary. So in particular, it can be the honest one, will accept, or so it seems. So soundness and zero knowledge are in, you can say, a creative dissonance with one another. So where is the difference, where this argument in particular breaks? So that basically sketched some intuitive arguments that zero knowledge proofs cannot exist, or that if they exist, then they are not sound. Because if you can simulate, then you can cheat in the proof. Just run the simulator, and you don't know whether the statement is true or wrong, but you can. This is an efficient algorithm, so just run it, and you would be apparently convincing the verifiers on it. So here is the kind of a trapdoor that allows to separate these and see that actually simulator can do something, but a real cheating prover cannot do that thing. And the trapdoor is that a verifier, we're going to, without loss of generality, we're going to think of this as a randomized algorithm. So it has some random tape input. And basically what I will be saying therefore is that if the verifiers are deterministic, then you know, unless you have some other elements in the model, like a random oracle, which is basically like a source of randomness for everyone, then zero knowledge proofs would be impossible. But that's not something new. You know, you can see that basic encryption cannot be secure without randomization. So if okay, so in a standard interaction, this tape is taken from a random source, and a verifier's view consists of the messages that he gets from the prover and this random tape. And that's the view. So the transcript goes over the randomness of V star and randomness of the prover. Right? So there is some random choices that this guy makes without loss of generality. And both of these randomnesses, the local of the verifier and the prover, they determine the distribution of these messages, and these form the transcript, or well, I guess interaction, because transcript is a technical term that really refers only to messages exchanged on the wire and not some local information. So the simulator on statement will create these messages, and he will create the first one. Let's say that we're talking about protocols that prover starts. So simulator will create this first message, but simulator will also produce this. So in the simulation, this is this set by the simulator. And when we argue that something is a zero knowledge proof, we will compare the distribution between the message and the random tape here and the messages in the random tape here. And we'll say, okay, this has to hold for every V star. So no matter what V star is, what it does, as long as it's efficient, the goal is to create an emulation procedure that makes this tuple indistinguishable from this tuple. Now, it's a little bit a philosophical thing as to, okay, so first of all, note that this is something that a real prover, that if you are an honest guy who's interacting with some cheating prover algorithm, and your concern is soundness. So you are interacting with possibly a cheating prover, and perhaps this prover runs this simulation algorithm. But well, that's not very useful, because the simulation algorithm will basically, if a proof system is sound, it is necessary for them to modify the local randomness of the verifier. Because if the only thing they do is just manipulate these messages, well, then that means that the proof system is not sound, because that's what the standard, just a network cheating prover could do, right? He could determine these messages any way he wants, in particular following this algorithm. But the cheating prover cannot modify, my own randomness. What is this randomness? Okay, let me give you an example. Let's say you want to identify somebody in this way using public key encryption. So you have their public key, and you want them to prove that they have the corresponding secret key. How about you encrypt a random nonce and send it to them and say, can you decrypt it? If they decrypt it and send you back that nonce, perhaps do it over and over, then this will convince you that you are talking to somebody who has the secret key, because you just encrypted random 100-bit string. There is no way this 100-bit string ever occurred to anybody else, right? Because it's 2 to the minus 100 that you hit it, that somebody else hits it. So if you see the same nonce coming back, that means that you're talking to somebody who has the decryption key. It's an interactive identification scheme. It's not exactly like a zero knowledge, but it's close. It is, but you can see how randomness of the verifier was absolutely key in designing this proof system, the proof that I'm talking to an owner of the secret key, right? It was precisely the randomness of these nonces that allowed me to have any handle. I picked a random nonce, I encrypted it locally, and these are my messages, it's a ciphertext. If the same nonce comes back, I'm glad. Why? Because I believe that this random nonce I chose, is really mine. It's closely kept. Nobody, an attacker cannot interfere with this. It's like my local secret in this proof system. But you can also see that it will be easy to simulate, because a simulator that does not have, he would give me on a random tape, write this nonce, I would encrypt it, and of course he knows how to respond to that, because he wrote this himself, the simulator did. In that sense, this interactive identification scheme is zero knowledge. Okay, but it's not, it's zero knowledge only if I remove the star. So only if I'm talking about an honest verifier who does the prescribed algorithm. So he just takes a random nonce and he encrypts it. That's a special case called honest verifier zero knowledge. Zero knowledge, but only to people who follow the algorithm. Only to verifiers who follow the algorithm. And that simple interactive identification is not zero knowledge to an arbitrary algorithm who might form this ciphertext in an arbitrary way. In particular, he does not know what it encrypts. He sends ciphertext and gets back decryptions, and he forms the ciphertext somehow differently. We don't know how he forms it. He's an arbitrary algorithm. You can think whether the CCA secure encryption would imply a zero knowledge identification scheme created along these lines, but let's leave this as an open problem. So yeah, so it's all about the randomness of the verifier, and why does existence of such an algorithm, does this really work in this example, right? Where I said, okay, I can replace a signature with a simulation, because if this is an adversary, well, he has some random tape. So if the simulator fixes this random tape, and if the combined view of the random tape and the proofs is indistinguishable between what this adversary would expect and the simulation, that's fine, right? The same argument basically goes through. indeed, I can replace a signature with the true random tape of the adversary with simulated signatures, and the simulation actually also manipulates random tape of adversary. It just creates a new adversary who just does all of this on a public key. Okay.
Professor?
Uh-huh.
So it's not that simulator exactly talks with V star. He simulates the whole interaction. So couldn't we think of it as not two protocols interacting, but just a simulator giving you a view? So replace both of them with one only.
Okay.
Wouldn't it be better? Because it seems like you are...
So wait a second. So I'm arguing that if this proof, if what happens here is a zero knowledge proof, then by definition of security of zero knowledge property of the proof, in here I will be able to replace proofs created by a signature by proofs created by the simulator, except that simulator will also have to have a way to manipulate adversary's local randomness, but he will. And the fact that he does not change the logic of this argument. So that was what I was sketching.
Yeah, but I'm not exactly talking about this specific case. I'm just thinking about the definition of zero knowledge.
Okay.
Couldn't we just think of one algorithm having access to ST and simulating the view of V star when interacting with P?
And not having this?
No, not having sim and V star, only sim.
Oh, like locally interacting.
Yeah, he just thinks inside his head that he does things inside his head and just outputs as if the view was with V star.
Yes, so we will see in a second that, well, I don't know if in a second, but we'll see that in a random oracle model, you can make non-interactive proofs, in which case this verifier is really moot. Like, it doesn't matter what the verifier is, and I don't need to talk to him when I create a zero knowledge proof, because it's a non-interactive proof. So I just, if I can emulate the bit string that represent a non-interactive proof, I don't really need to talk to him. I just output that bit string.
Okay.
But it's also possible in the standard model, but it's much less efficient and yes, except but there are interesting cases of more efficient non-interactive zero knowledge proofs that come from bilinear maps. So yeah, but you know, talking to V star is not like because in a proof you start of security of anything, you start by saying, okay, let's assume that some adversary exists, and from then on it's a box, and everybody can use this box. So the box exists supposedly. Let's call it A. In this case, this box is part of the box is doing verification in a zero knowledge proof. Everybody is free in the security proof to use this box to their content. It doesn't mean really talking to a physical attacker. It's if the attack exists, then therefore there exists some efficient algorithm that performs it, and we can say, okay, so therefore this must be some polynomial time machine. We can use this polynomial time machine locally without talking to an actual attacker on a network. Okay.
Right. I think my question is more about you need to follow the logic of V star to some degree if you are doing things like this.
Yes.
Right?
Yes. So
kind of modifying.
You would have to. Right. It would not. It would, you know, it's not for general algorithms. You have to know what V star does in order to set this randomness correctly and then emulate these messages. Yes, it will all be specific to V star, and the way simulator will do it by running V star locally and trying it on different inputs and somehow getting this view from that. Let me try to do example of this will be a non-interactive zero knowledge, and it will be non-interactive into random oracle model for some hash function h. Okay. So in other words, we have some language, and the verifier will have the statement for this language. The prover will have the witness. There will be a random oracle h that everybody can access, sending some messages and hashing them and getting back the hash outputs. But it's a random oracle in the sky. So we just pretend that the hash function like SHA-256 is this perfect source of randomness that anybody out on the on the planet Earth and beyond can use. And that running SHA is like sending the inputs to this random oracle and seeing what it outputs. And the verifier can do so, the prover can do so. Based on this interaction and the witness, the prover is going to send just a single bit string called a proof. So P is going to be called proof, but it's a bit string. Okay, and based on the proof and the statement and interaction with the hash oracle, this guy is going to accept or reject. Okay. Now, correctness, soundness, and zero knowledge all modified so that probabilities go also over random choices of this random oracle H. Okay, so for example, in the notion of zero knowledge, when I look at the randomness of, when I look at, okay, the transcript and the randomness have to be distinguishable in the real execution from transcript and randomness in output by simulator. But all of this the verifier will also talk to the hash function. And now the randomness will involve all three. That's one. First of all, probabilities go over this. Second, in a zero knowledge game, H will be emulated by the simulator. So in a zero knowledge game, we'll say, okay, this is an attacker, and he talks to a true good hash function and a good prover. And we'll change both of them by the simulator on a statement in a zero knowledge proof. In other words, the simulator will basically have much more power, because not only he will be, in fact, we will not care about any internal randomness of the star, just a much more stronger thing, that the simulator has a control over this random beacon in the sky. He can embed some things in the answers of the hash that are correlated in the way he forms his proof. And that will give him a trapdoor that will make this stuff indistinguishable from what the honest proof verifier, from whatever this verifier sees when it interacts with the hash function and an honest prover. But the difference, of course, is that simulator has only statement and the honest prover has the witness. So this is like g to the x, and this is the x itself, the grid logarithm. This is the public key, and this is the private key in the signature case. And in the Soundness game, we flip. Age will be, will be honest. So now the cheating prover will face a double team of an honest verifier, but also a random oracle. And we'll use this power that is a random oracle to argue that the proofs cannot, that it's a negligible probability that you end up proving a wrong statement. So just like this little local randomness in a standard model allows us to create essentially a cheating procedure for the efficient simulator if he has access to this. And it's a cheating procedure that nevertheless does not break soundness. So if somebody doesn't have access to this, then they cannot convince a verifier on the wrong statement. This is an extreme case. The random oracle in the sky here will be used by the simulator strongly to help the simulator quote unquote cheat. But it will, when you consider soundness, you flip the team for which the random oracle works. Now it works on the side of the verifier to keep the prover honest. In the zero knowledge case, the random oracle worked on the side of the simulator to show that proofs leak no information. Yes? Okay, so finally, and this proof, right? Okay, so let's take a statement to be y g to the x and the witness x. And the relation, the language is, well, actually, it's hard to talk about the language because in some sense, every group element is in the language, but the relation is a pair of yx such that y is g to the x. Okay, and we assume that g is public parameter, so it parameterizes this language. Okay, here is something that they could do. The prover has this input, the verifier has this input. Okay, the prover is going to pick a random x prime in the ZP. So, by the way, x was an element in ZP. Yes, and send y prime, which is g to x prime. The verifier will respond with a challenge that is a hash of y and y prime, where this hash is an arrow that takes any messages, group element in this case, and outputs element in CP. And this is the challenge that the verifier sends back. Okay, but there's cutting to the chase. he doesn't really need to send it because the prover, he knows X, so he can compute Y, right? Just taking G to the X. And he knows Y prime, so the prover can compute this locally. So in fact, C can be computed locally by the prover, and this is not really needed because I'm showing it to you in the random oracle. These proofs also exist in a standard model where they are interactive, but their analysis is more complicated in this case. So, but that's where they came from an interactive proof system where this was sent and a challenge was sent back. In the random oracle model, this way of locally generating challenges by both prover and verifier, and it's the same one, suffices and makes this proof system non-interactive. And then he creates a final response, which is equal to x prime plus xc mod p. And he sends that. Now, this guy accepts or not, accept even only if, what does he do? He takes the g to the z, and it has to be g to x prime plus g to the x times the c. So g to x prime is y prime, and g to the x is supposedly this y. And finally to the c, right? And if this stuff is formed correctly, then this would be equal to g to x prime times g to the x to the c, which is g to x prime plus xc, and it's correct, right? Because this is a group of order p, so all the operations in the modulo in the exponent are mod p. And reject otherwise. Okay, so that's it. That's the proof system. Because in the random oracle model, the challenge can be computed locally. So in fact, this can be combined, and this is the proof. So the proof is y prime z such that first such that g to the z is y prime times y to the c for c, which is the hash of y and y prime. Let's argue that this is zero knowledge. Arguing soundness will require actually one more building block, which is called extraction. The idea behind the extractor, because the thing about these proof systems is that everything is in the language. So every group element has some discrete logarithm. So sort of soundness is a moot concept. Every y is in a group. So what does it mean that a prover cheats? Well, we'll have a notion of an extractor, which if a prover creates these proofs, then there is an efficient extractor machine that is going to actually extract this witness from them. And in the final security analysis of the signature scheme, this is why the signature scheme is as secure as this discrete logarithm, because if somebody who, this oracle is replaced by simulator, that's a zero knowledge property, we will argue that. But if they output a forgery, then this is a new zero knowledge proof. And an existence of an extractor would mean that that any machine that can create such proofs, the extractor will extract a witness and the witness is the secret key. And now finally you have the reduction that you combined simulator and extractor and the attacker, which show that there is some efficient process which, given the public key, outputs the secret key, the witness in the statement, right? Which is so this is the secret key in our case, and this is the public key. Okay, so that we will have to postpone that to the class where you learn about these things in a more systematic way. But let me just complete with the argument for zero knowledge. So here is the simulator, which whose only inputs is y, and but also can control the random oracle h. Okay. So the simulator will proceed like this. Very simple procedure. First, pick random z in CP. So pick the random response. Compute this first message in the way that fits the verification equation. Set y prime to be g to the z times y to minus c, right? Then the verification equation verifies, right? Because if that's the y star I'm putting here, then y minus c, y c cancel, all I'm getting is z, right? So it will work. And finally, set the random oracle output on inputs y and y prime to be c. Sorry. So pick z, okay, and pick c at random in CP. Okay. And where could you go wrong, basically, right? So this simulator, who controls the hash function, will send proof as a pair y prime z to even an arbitrary verifier. Well, this is what can the verifier do with this thing? Well, it can query the hash function. That's the only other thing in the world it can talk to. And if it sends, so it also learns the statement, at the very beginning. So if it sends the y prime pair, well, it's set to be c. So this view agrees. You can see that why are this triple z, c, and y prime exactly like the z, c, and y prime in the execution? Because let's first look at how is the z distributed. It's uniform mod p because x prime is a one-time pad. So rather than think of y prime as created first, I can think of z as created first, and then y prime is whatever whatever satisfies this relation. The only missing piece is the c, which is here I choose y prime first, and I set c to be an output of the random oracle on these inputs. And here I switch. I first choose the c. Based on that, I choose y prime, and then I patch up the output of the random oracle. But how can anyone see the difference if the random oracle h is this big, table in the sky, for first version, second version, third version, etc. And each of them have random values, right? So what can this verifier do? The only hashes of interest are those that contain this y value, but it can hash many different y primes. Perhaps if it hashes this y primes on a huge amount of these, then it sort of blocks the simulator from setting this value on any y prime that was previously hashed. Yes, the simulation would not work because this hash value was already set somehow. But clearly, in a discrete log, this group generated by G, right, is a large group. It has to have, super polynomially many elements. So no matter how many polynomial this guy hashes, because this y prime is random, right, by the choice of the NC, this is a random element. The probability that it was hashed by the attacker is negligible. So simulation, basically picks a random row here, and of course it can set the corresponding value in a random way, in any way it chooses. Well, it has to be random, but it is. C is a random value, right? You can see that there are some funny dependencies. Is this C determining both the input and the output, therefore creating some correlation? Well, yes and no. Yes, it is, but however, it's completely randomized by the Z, the input. So Y prime and C are independent. If I'm just looking at that relation, only. Yes. So this input and an output in the table are independent, which is a good thing. So zero knowledge, okay, a complicated object, not the easiest object in cryptography to work with. Nevertheless, it gives efficient signature schemes. This is how signature schemes are created on elliptic curves and in discrete log crypto systems, using prime residue groups. And they are rather efficient because signing, okay, how do I actually convert this to a signature scheme? It's very simple. I add the message M to the hash. So the only movement from the non-interactive zero knowledge proof based on random oracle and signature scheme is add the message to a hash. So it will be added here. Okay. How efficient is the signing? One exponentiation and a linear relation and a hash. So this is a fast operation, just hash your message. This is a fast operation, addition mod p and mult mod p. This is an exponentiation, but this is like half of the Diffie-Hellman key exchange. So this is the most basic public key operation, right? A single exponentiation. Verification, it used two exponentiations, but actually they can be combined because I can move this to the left side and run an algorithm that is called multi-exponentiation, that they compute a product of exponentiations with two different bases, two different exponents. And if you look at how exponentiation algorithms run, running so-called multi-exponentiation with two bases is not much more costly than a single exponentiation. So roughly speaking, it's one exponentiation per party, but it's rather a minimal cost for a public key crypto system. It's also very short, the signature, right? A single group element and NSEP, right? So this can be 320 bits, okay, on a 160-bit elliptic curve. Okay, so sorry for going 10 minutes longer. Let's tell me if you have some questions on this.
So next quarter, we will start with zero knowledge?
Yes. Yes, I believe it's an essential tool in any cryptographic protocols. So, so that's the first tool to understand secure computation and so forth. Everything uses zero knowledge, authentication. You know, simple tasks like authentication, more complex tasks like secure computation uses zero knowledge. So this is the first thing. And also the way that the zero knowledge is that the way you learn how to think about security is in a sense, secure computation is a generalization of the same paradigm of simulation on one hand, extraction on the other. So that's why it's the place to start. Some other topics which I think would be yeah. So apart from all sorts of different methods for secure computation, I want to look in particular about privacy preserving computation like private information retrieval, oblivious random access memory, and yeah, and associated tools. Another very key machinery that allows creating secure protocols for all sorts of tasks is something called Oblivious Transfer, and so that's another. It's sort of similar to it's similar to zero knowledge in some way, but it's like if zero knowledge are signatures, then Oblivious Transfer is a generalization of encryption. And both of them have all sorts of wonderful uses. So we'll learn these tools, and we will learn applications that use them, starting from approaches to secure computation, and then for more specific tasks. Okay, well, if there's no further questions, then thanks for taking part, and I'll see you around, and I will also interact with you when I grade your homework. Okay, so take care for now. Thank you.